This code loads data from the data x to data 1.txt file. Xtrain holds input features while ytrain holds the labels. This code prints the first 5 elements of the Xtrain array and then shows the data type of Xtrain. This code prints the first 5 elements of the ytrain array and then shows the data type of ytrain. This code prints the shapes of the Xtrain and ytrain arrays. Additionally, it indicates the number of examples in ytrain, display the total number of training examples. This code plots the data using Xtrain and ytrain. It labels the accept and rejected examples with post label and snake label. It also sets labels for the X and Y axis, adds a legend, and display the plot. This code calculates the sigmoid function for a given z values that can be a scalar or a numpy array of any size. The function returns the sigmoid value, maintaining the same shape as z. This code calls the sigmoid function with an input of 0 and prints the results. That is the sigmoid value of 0 is displayed. This code calls the sigmoid function with the array -1, 0, 1, 2 and prints the result. Then it runs the sigmoid test function to test the accuracy of the sigmoid function. This code defines a function that calculates the cost for given data. X in the input data, Y is the target values, W are the model parameters, and B is the bias value. The function calculates the loss for each example using the sigmoid function and finds the total cost. The result is the average cost of all examples. This code retrieves the dimensions of the Xtrain data sets initial W and initial B to zeros and then calls the compute cost function to calculate the cost with these initial parameters, printing the result. This code calculates the cost using non-zero test W and test B values. The test W values are set to 0.2 while test B is set to -24. The cost is computed using the compute cost function and the result is print. Then the compute cost test function is run to test the accuracy of the function. This code defines a function that calculates the gradient for logistic regressions. X is the input data, Y is the actual values, W are the model parameters, and B is the bias value. The function calculates the error by finding the sigmoid value for each example and uses this error to compute the gradients for W and B. As a result, it returns dw and dgdb, which are the cost gradients for W and B parameters respectively. This code calculates the gradient with a W and B values initialized to 0. The compute gradient function is called the option dgdb and dgdw, which are then printed. This code calculates the gradient with non-zero test W and test B values. The compute gradient function is called the option dgdb and dgdw. The results are printed, and the compute gradient test function is run to test the accuracy of the function. This code defines a function that performs gradient descent. To learn the parameters, it updates the parameter by taking them iters. Gradient step with a given learning rate. For each iteration, it calculates the gradient, updates the parameters, and records the cost. It also prints the cost regularly at regular intervals. The function returns the update WB, cost history, and W history for graphing. This code starts the gradient descent process by setting a randomly initialized W vector and a B value of -8 using a specific learning rate and the number of iterations. The gradient descent function is called to update the model parameters. As a result, update WB values and cost history are obtained. This code uses the plot decision boundary function to draw the decision boundary over the training data, visualizing the model's classification performance. This code makes This code makes prediction for the given X data using the learning logistic regression parameters. The sigmoid function is computed for each example, and results are classification as 0 or 1 based on the threshold of 0.5. Prediction are returned in the P array. This code generation random TMPW, TMPB, and TMPX values to test the prediction function. The function makes prediction based on this input, printing the shape and value of the results. Then the predict test function is run to check the accuracy of the function. This code calls the predict function to obtain predictions on the training set. Then it calculates the accuracy by comparing the predictions to the true labels and print the training set accuracy as a percentage. This code loads data from the data X to data 2.txt file. Xtrain contains input features, and ytrain contains target label. This dataset is commonly used for training models in machine learning applications. This code prints the first 5 elements of the X-terrain and Y-terrain arrays. It also shows the data type of both array, which is useful for ensuring that the data is loaded correctly and understanding its structure. This code prints the shapes of the X-terrain and Y-terrain arrays. Additionally, it shows the value of m indicating the total number of training examples. This is helpful for understanding the size of the dataset. This code visualizes the training data using the plot data function. Positive examples are labeled accept, while negative examples are labeled rejected. The y-axis is labeled microchip test 2 and the x-axis is labeled microchip test 1. A legend is added and the plot is displayed. This code retrieves the original shape of the X-terrain data and uses the map feature function to expand the features. Mapped X holds the array of expanded features and the shape of this array is printed. This helps the model learn more complex decision boundaries. This code prints the first element of the X-terrain array and the first element of the mapped X array. This is used to visually compare how the feature expansion process occurs. This code calculates the cost considering regularization. It first finds the cost without regularization, then calculates the regularization cost using the sum of the squares of the model parameters. The total cost is the sum of these two values. This code creates X-mapped by expanding the features, sets random initial parameters, and calculates the regularization cost. The calculate cost is prints and the equivalency of the function is tested. This function calculates the gradients considering regularization. It first finds the base gradient and then updates it by adding the regularization term, the term for each parameter. It returns the bias and parameter gradients. Xmapped creates the expanded features. Random initial parameters are defined along with a regularization constant. The regularization gradient is calculated, and the first 5 elements of the bias gradients and parameter gradients are printed. The accuracy I don't know, of the function is just. After setting random initial parameters and the regularization constant, the gradient descent function is called. This updates the model parameters and returns the cost history. No. Cost history. It draws the model's decision boundary. Finally, it calculates the model's accuracy on the training set and print it as a percentage. Thanks for listening.